Okay, we're going to get into electron configuration. Specifically, electron configuration, what it does, it kind of fleshes out exactly what are in the energy levels. So, for example, we know in a Bohr model, we represent the energy levels like this, right? So these are the shells around our nucleus. Now, the question is, where exactly are these electrons within the? So, for example, let's say there are 4 electrons in the third shell or third energy level. Where exactly are these? Where exactly are these electrons located within the third energy level? So, what we're going to do is we're going to look more closely at the third energy level, or the energy levels themselves. All right, so each energy level has different sub-levels, and so each sub-level has a different orbital. So if you think of this as rooms for these electrons, it has different sub-levels. So right here is the S sub-level. It has one orbital. So within this orbital, think of it kind of as a room. You can fit up to 2 electrons. So each orbital fits up to 2 electrons. Here's the S orbital. And then the P sublevel has 3 orbitals. So here's the P. It has 3 sublevels. It has 3 orbitals. And then here's the D. So within these areas, here, and here, what you see is the probable location for the 2 electrons that fit in the orbitals. And then here you have the Fs. All right. So it's important for us to know within the S sublevel we have 1 orbital, the P sublevel 3 orbitals, the D sublevel 5 orbitals, and the F sublevel 7 orbitals. Okay, so let's fill this in. But before we do, some rules we need to know. The first is the energy level equals the number of sublevels in that energy level. And the second rule is the number of in each orbital you can fit a maximum of 2 electrons. Okay, so for example, in this first rule, in the first energy level, we can only fit, since it's energy level number 1, so this is the N value, there you can only fit 1 sublevel. So in the second energy level, the N is 2, so you can fit 2 sublevels, 3 sublevels, fourth energy level, 4 sublevels. The sublevel that is first filled is the lowest energy. So if you remember from the previous slide, the lowest energy is S. And so since we only, in the first energy level, since it's only N equals 1, there's going to be only 1 sublevel. And if you remember from the previous slide, the S has 1 orbital. And remember, within each orbital, there are 2 electrons. So the max number of electron is 2. So in the first energy level, we can only fit 2 electrons. And this makes sense because if we remember in the Bohr model, you can only fit 2 electrons in the first shell anyways, or the first energy level. In the second energy level, you can fit 2 different sublevels. So the lowest energy is S, but now you can fit the P. The P, if you look at the previous slide, P has the has the second least amount of energy. All right, so how many total number of orbitals in the second energy level? Well, you would have 1 orbital from the S sublevel, and add that with the P's. So with the P's, you have 3 sublevels, or 3 orbitals, I should say. And so this equals 4. the total maximum number of electrons. So if I have 4 total orbitals, each orbital can contain 2 electrons. I have a max of 8 electrons. Third energy level, 3 sublevels can fit in the third energy level. This is S, P, and D. The number of orbitals, so for S you can fit 1 electron, or sorry, 1 orbital. P is 3 orbitals and D is 5. So 1 plus 3 plus 5 gives me 9. Maximum number of electrons, if I have 9 orbitals, I'm going to have 18 electrons. And then when n equals 4, this is S, P, D, and F. The number of orbitals in each sublevel is 1 for S, 3 for P, 5 for D, and 7 for F. Add those up. The total number of orbitals are going to be 16. 16 times 2, because there's 2 electrons in each orbital, is a max of 32. By the way, I just want you to notice that these correspond to that 2n squared value that we talked about earlier when figuring out the maximum number of electrons in each energy level. If we go back, hopefully this starts to make sense, the image we're looking at, where this is your S orbital, or this is your S sublevel, right? And so there's only 1 orbital. You can fit up to 2 electrons here. And then here, this is your P orbital, and you can fit 6 electrons. In the D orbital, you can fit 10. You have 5 orbits, or orbitals, so you can fit up to 10 electrons, and so on. These are actually the images of each orbital, and so remember, Schrodinger basically said that we don't know exactly where the electrons are, but we can kind of predict where they probably are. So basically, these little, some of them are spheres, but these 3-dimensional locations or rooms are the area that we believe those electrons to be, the 2 electrons in each orbital. Okay. Here are 3, so what we're going to do now is we're going to start to fill these electron orbitals, but there's rules in the filling. The first is we must fill from the lowest energy to the highest. So each electron occupies the lowest energy orbital available. That's the Aufbau principle. The Pauli exclusion principle, you have a maximum of 2 electrons in each atomic orbital, and then the electrons must have opposite spins. And finally, Hund's rule says that the single electron with the same spin must occupy each equal energy orbital before additional electrons with opposite spins can occupy the same orbitals. That's quite wordy, but let's go ahead and I'll talk about, as we do examples, I'll go ahead and integrate each of these principles or rules. The first rule is the Aufbau principle, and it basically says you must fill the lowest energy levels, or the lowest orbital levels. And so to help with that, what we do is we use what's called the diagonal rule. So in order to create the diagonal rule, the first thing you have to do is you have to list out all the orbitals. So the first lowest energy orbital is 1s. So the first is 1s. So remember, in the first energy level, you can only fit the s orbital, only 1 orbital. So we put 1s, and that's it for that line because that's all we have. So the next one is 2s. Remember, the second energy level we can fit a second one, so that's 2p, 3s, 3p, 3d. In the third energy, we can fit 3 sublevels, S, P, and D. 4, we can fit 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. Now, at this point, if you remember the rule, if I have the fifth energy level, I should have 5 different sublevels. The fifth sublevel is 5G, and the reason why with no G, you don't have to know this, but it's G after the F orbital. What they did is they just made it alphabetical. So FG. So if I do 6S, 6P, 6D, 6F, 6G, so FGH. So this would be 6H and so on. So we can do, let's do 7S, 7P, 7D, 7F, 7G, 7H, and 7I. Okay? All right. Now, we have to write this out first, and then we use what's called the diagonal rule. Just to show you, we start with the 1S, but we're going to count diagonally. So it's going to look somewhat like this, and I'll show you what I mean. Okay. Now, what does this mean? So we always start here. So the lowest energy level is 1S. And then I start, so 1S, that's it. There's nothing like this way, so to speak. So the next one is, this is my second one. So this would be 2. So the next one is 2S. So this is your lowest energy. So the electrons would fill in this order. This is 3. I have 2p and then 3s, right? 2p right here and then 3s. So this is your fourth. It'd be 3p, 4s. And then here's your fifth. 3d, 4p, and 5s. So I just did this one. And then the next one is 4f, 5d, 6p, and 7s. Now, this is from lowest to greatest energy level. So 7s has a high energy level. We're going to stop right there. And you can keep on going if you wanted to, but I just wanted to point out some interesting things. What I want you to notice is the third energy level. You would think that after 3p you would fill 3d, but really what happens actually is after 3p is 4s. So 4s actually is a lower energy level than 3d. And so this is kind of interesting. And this is not something Bohr predicted, but when we look at the energy levels for each of these, 4s actually has a lower energy level than 3d. You can see that same thing here when it comes to, so here we have 4p, and then 5s, and then we go back to 4f, which is weird, right? You would think, oh, you should do 4p and then 4f, 4d and 4f, but you don't get that. So it's kind of a weird thing going on here. I think I might have, did I skip something? So I got 5s. Oh, I did skip something. I'm sorry. So let me go back really quickly. So what you might have noticed I did wrong, and sorry about that, is after 5s, which is right here, I think I skipped, and I should have known that. So next one is 4d, right? So 5s, and then I start here. This is 4d, 5p, 6s. So I just ended there, and then 4f. So next is 4f. Nonetheless, what I wanted to show you was this 5s is before the 4d, right? So the 5s is before the 4d. Okay? All right, so we're going to use this to help us. Let's do a couple example problems, and hopefully this will make sense. All right, so let's do, for example, I want the electron configuration for lithium. So lithium is Li. All right, so for lithium, if I look at it, has the atomic number 3, so it has 3 electrons. So I will start with my lowest, which is 1s. And what I'm doing is I'm drawing these orbitals. I draw these orbitals as lines. And then, so what I'm going to do is 1s. I'm going to fill it. Now, electrons have spin. So they just need, what you need to know is if they're in the same orbital, they should have opposite spin. And that's the only way they will, so you cannot have two electrons with both up spin or both down spin. So here I'm showing, this is what I mean by up spin. And then this one is down spin. And so what I'm showing is they have to have opposite. And this is what Hund's rule states. Okay, all right, so I filled 2 in my first S orbital. So I still have more space, so I'm now going to do 2s. 2s is my next one. And I just need 1, so I just put 1 electron. And so this is 1s2, 2s1. So just to break it down, first energy level, s orbital, has 2 electrons. The 2 looks like an exponent. And then 2s1. Second energy level, s orbital, only 1 electron, even though you fit 2. So the electron configuration for lithium is 1s2, 2s1. All right, let's do another one. Let's try carbon. So carbon has 6 protons, so the neutral atom has 6 electrons. Our lowest energy level, according to Aufbau's rule, we need to fill in our lowest, which is 1s. So I'm going to fill it in with opposite spin. That's Hund's rule, right? So I have 1s. That one's full. Oops, sorry about that. But I still have 4 more electrons, right? So my next one is 2s. So this goes up and this goes down. I have 2 more electrons. If I look at the diagonal rule, 2p is my next one. 1, 2, 3. Now 2p has 3. The p orbitals have 3 orbitals, right? So the 2p sublevel has 3 orbitals. I have 2 electrons remaining. If you read the Pauli exclusion principle, or excuse me, I'm sorry. Let me back up really quickly. I misspoke. What I should have said is the Pauli exclusion principle is where you have opposite spin. And then the Hund's rule, no, I'm right. I'm sorry. Hund's rule is with opposite spin. And then Pauli exclusion is, so Pauli exclusion, what occurs is the same spin needs to fill in once. Now, if you think about electrons, they're negatively charged, and so therefore they're going to repel each other. They want to stay as far away as possible from each other, right? And so the Pauli exclusion principle, if I have 2 electrons remaining here in carbon, I could fill it like this. But what they do want to do is they want to repel each other. So instead of doing like this, they're going to separate into orbitals that are far away from each other, and they're going to have the same spin. So that's what's called the Pauli exclusion principle. So sorry if I confused you. So let's just review. So the Hund's rule is when they have opposite spin, and they can only fit 2 in the orbital. The Pauli exclusion principle is that when you fill multiple orbitals of the same sublevel, so in this example 2p, you must fill with the same spin on each orbital before you can go back and fill with the opposite spin. Let me give you another example, and hopefully that might clear it up for you guys, okay? So let's just do, fluorine. Fluorine has 9 protons, so it has 9 electrons. So I'm going to fill first, according to Aufbau principle, with the lowest energy level, or the lowest orbital. And so here's 1s. I'm going to fill with opposite spin, and there can be only 2 that fit there. So therefore, this is what's called, this is Hund's rule, right? All right, so 2s. So I've now filled in 4. I'm now going to go to the 2p sublevel. In the p sublevels, we can fit 3 electrons. I'm sorry, 3 orbitals. Now, I have 5 electrons remaining, right? I have 2 here, 2 here. That's 4 that I filled in. I need 5 that still need to find a home. And so what I'm going to do is I'm going to fill it in. Now, I'm going to fill in according to the Pauli exclusion principle. I have to fill each one in first, right? Because they want to be far away from each other. But I still have 2 remaining electrons, so I'm going to go back and fill in these, okay? And so this is what it looks like. All right, so if you must fill each orbital first with 1 electron with the same spin. I chose up. Like, if you had done this, there's no problem. If you had done this and then gone back and then did that, not an issue at all. That's the same thing. It's still following the Pauli exclusion principle. I just chose my spin up versus spin down, but it doesn't matter. All right, hopefully that's helpful.